Well, hello. We're going to talk a little bit about some things that are going to be very helpful in understanding geologic maps today. And I've titled this presentation. It's an agglomeration of stuff I use with other courses. So the slides will look really inconsistent, but you know what? We'll deal with it, right? Such as this such as the time. So we call this stress, strain, and geologic pain. And how do we tell what kind of pain is going on? We look at the geologic map, and that tells us something about the history of these environments and what they've been through. It's like a record of that pain over time. So if we look at, if we go to a place like this is out in the Four Corners region, Colorado Plateau. This is the Wingate Sandstone, Moenkopi, Chinle, and so forth. These are classic formations. If you ever go out there and do geologic mapping, you get to learn all about them. But you see sequences here of different geologic layers. Here's one, a sandstone, another sandstone, some shales, and so forth, all deposited in some kind of ancient basin sequentially. Initially, these were all loose sediments, as you all, I'm sure, know by this point, and then they were lithified. And subsequently, these didn't, from what you can tell in this image anyway, didn't really have much in the way of tectonics acting on them. Of course, they did. This is the Colorado Plateau. It's been uplifting for tens of millions of years now, as the Colorado River has been cutting down into it, creating something called the Grand Canyon. You can't see that in this image, of course. This is just a snapshot of one location. But anyway, this is about 6,000 feet up. So, of course, that means that there's been tectonic stuff going on. But that's all an overprint of stuff that was placed on these rocks afterwards. And so, if I'm going to tell the story of these ancient environments, I'm going to start with the sediments that are laid down at the bottom first and work my way up to the top. And then I'm going to focus on things that cut across, like faults and folds and things that tell me something about the subsequent story of these environments, leading to the final discussion, which is really looking at what this environment looks like today and how this location looks the way that it does. And so that's kind of where we're going with this. Ultimately, I want you to look at a geologic map, a two-dimensional representation of a model that is of a three-dimensional reality, and be able to tell the story. So we're going to do that using relative dating principles. And of course, in this case, I don't know why this is so massive here. Relative dating principles are basically nothing more than placing events in a sequential order without the use of absolute age dates. Absolute age dates are things that we calculate using radiometric dating. We'll come to that in a couple weeks, and we'll do a little math fun with that. But so some basic principles. One is, of course, that stuff that lies below other stuff is older than the stuff lies below. That it lies below, rather. That's what we call the principle of superposition. We also originally assume that the sedimentary layers were deposited in a horizontal fashion and in a laterally continuous fashion to a certain point. Of course, lateral continuity extends only so far as that particular environment extends. The biome, however you want to refer to it. The biome is not the right term, of course, but you get the idea. Environments don't continue on forever. But when we're looking at them from the geologic record, for any given location, we can assume that there's some continuity off into the distance. So over time, this allows, the understanding of these relative principles allows us to understand the history of an environment from a very basic sense, or a location rather, the environmental changes at a location. The final one that's important is cross-cutting relationships, and this becomes really important, especially when we talk about tectonics and the tectonic overprints that put on the rocks later on through various strains and stresses. So, of course, you have things like igneous dikes that make their way intruding through rocks. That's what this is here. Or you have faults that come later on. Those are examples of forms of strain that result from a stress being placed on the rock. You all know what stress and strain is. We'll get to that in a moment, in a second. Another important principle that's come along with this is the principle of fossil succession, and that is that based on evolutionary understandings, fossil assemblages succeed one another over a time in a predictable order. And as a part of those successions, we can find index fossils that are very helpful to understanding. These are fossils that live organisms that live for a short time, but then created tons of fossils, and that are really good marker beds to tell us something about the age of that unit. So then we get these things called unconformities, which is this really funny word. It basically just describes periods where there's stuff missing from the record. This could be because there was never anything deposited in the first place. or it could be because stuff was eroded away. And we have what was called, in either case, a hiatus or significant periods of time where there's nothing there. So again, non-deposition and or erosion. Examples of these include, here's some stratigraphic columns, and depo turns into rock. Some of it is removed by erosion. There's a hiatus, and then of course more deposition occurs later on. What this ends up looking like, and we represent it typically stratigraphically as just this curvy line. This is going to end up being what we call a disconformity, sedimentary, above and below, and it represents some amount of time, in this case several million years of time, where deposition wasn't occurring or where erosion occurred. And it'll end up looking in the final column like this. All right, so there's three kinds. There's disconformities where you have a horizontal unconformity where erosional place or lack of deposition that's separated by that separates two sedimentary layers. Angular unconformities are tectonically derived, and so they're produced first by typically by folding, and then erosion, and then deposition of another sequence of sedimentary layers. And then there's non-conformities, which are a little different. Not all these slides aren't all showing up for whatever reason, but anyway, what happens is you have deposition, then you have uplift and erosion, right? That occurs, and then you have more deposition, and you end up with what's called a disconformity, sedimentary to sedimentary. You can have deposition, uplift, and erosion, and then deposition again. And in this case, the uplift and erosion tilts the rock, creating an angular series of things, and you end up with an angular unconformity, and it looks like that. These are, of course, representations of the real world. They're models, right? Models are always wrong, but sometimes useful. And then we can also have nonconformities, where you have an intrusion of magma, uplift and erosion of the sediments, and then subsequent deposition, leading to what's called a nonconformity. Basically, that's where igneous or metamorphic materials exist below sedimentary materials that sit on top of the erosional boundary. So, the differences between these are somewhat subtle. The bottom line is that these represent periods of time where there either wasn't any deposition or the record's been removed by erosion and taken elsewhere. And we just don't know what was there. Filling in those gaps is pretty tough. One of the big ones is called the Great Unconformity. And really, it underlies all of the sedimentary layers that we have record of. And it goes back to about a little over 1 billion years. And that's this boundary over here. We have Precambrian metamorphic rocks sitting below Paleozoic sedimentary rocks. And this nonconformity can be found most places around the world, most critically in the Grand Canyon, but even locally here we can find it. Not so much locally here in Shenandoah County or Rockingham County, but if you go a little bit further east to the Blue Ridge area, you can find the Great Unconformity there. So if we apply these principles of relative age dating to sequences of rock, we can determine what order they were deposited in. We can even sometimes say something about how long it took to get that particular layer to be deposited, if we can talk about sedimentation rates. But ultimately, this is the first thing we wanted to understand in the interpretation of a location's ancient environmental changes, is understanding what's going on in the rock record. So typically we start with sedimentary deposition, can end up with the uplift, tilting, faulting, erosion, more deposition, intrusion of materials, uplift and erosion. It doesn't always occur in all this order, but these are cycles. You can think of it as a cyclical kind of thing. But again, not always in this order necessarily, but that's how you end up with complicated stuff like that. Or like this diagram. This is a classic thing we'd give to geology students to say, hey, what order did things occur in, right? And so you'd say from oldest to youngest, we'll start off with G because E is intruding into G, and then you'd go to 2, which is the fault there, and then you would go to K and D, and then you would go to O from there because that's intruding, but it's getting cut off, and then you would go from there to L, to A, and then maybe at that point you might bring in the fault 3 here, and then N subsequently, and then of course M, and then you have there's an unconformity here where you then bring in this next layer, B, I, and then actually I go back and look at O. O should be intruding in through all these, so I had that in the wrong order myself. See, I'm just kind of doing it off the cuff. But that's the idea. And followed by H, C, and F. And actually, fault 3 occurs almost one of the last things, and N then is the last intrusion. So again, I messed up. But you get the idea. So all of this happens, the subsequent stuff after deposition happens as a result of stress being put on the rocks. And typically this is because, when you're depositing the layers, the sediments in a basin, the stresses are relatively low, and it's mostly just an issue of the weight of the rock accumulating sediment and rock over time. But as the tectonic situations change, the stresses change as well, and you can get pulling and squeezing and twisting of rock to produce different kinds of results. So those are the stresses. The strains are the reactions to the stresses. So, if you have a lot of stress going on in your life and you get angry about it, that's a form of strain. Anger is a form of strain in that regard. So the stress can be directed, or it can also be just on all sides. We call this, lithostatic pressure, where it's being applied equally in all directions. And then there's, of course, directed stresses, which can have a squeezing effect or shear effect or a tensional effect. The most common kind of lithostatic stress is you end up ends up a situation at the bottom of the ocean where you end up with, you can squeeze styrofoam cups. You take them from their original shape, you're largely retaining the shape. Well, kind of. Obviously, there's some differences here, but generally, you're just making the material much more dense, and so what's happening there. But basically, different forms of strain have different effects. So, elastic deformation, eventually everything leads to fracture. That's the end point of all stress. So faults or breaks in the rock are sort of the end points. That's not the right number. This here and this here are where you surpass the elastic limit and even the plastic limit, and you end up fracturing or breaking an object. That's what we call brittle deformation. Before then, though, it's all elastic or plastic deformation. And there's a period of elastic deformation where if you deform a material, and then you take the stress off of it, it'll go back to its original shape, like a rubber band. At some point, you surpass what's called the elastic limit, and the deformation is plastic. And if you take the stress off of it, and it's in this regime someplace, it's going to retain the shape it currently had and not go back to its original shape. So as you increase the stress, the forms of strain increase as well. And they can be different depending on the intensity of the stresses, and also the speed of the stresses. You can have the stresses increase really rapidly, still the same effect, but so as you apply stress in scenario A, you're applying stress and you're in the elastic deformation. Then you move into the plastic realm here. In scenario B, you're looking at elastic deformation, and you never even enter the plastic realm, and you just ends up getting surpassing the elastic limit and breaking it here, fracturing it here. And C is very similar to A, but you just have a much longer period of plastic deformation. And this is mostly how rocks behave. So that's really important. But these are the different kinds of things you can end up with. If you take a test cylinder, and you put these in an apparatus and tested these things. This is all mathematically demonstratable in a lab. One of the forms of plastic deformation are folds. And of course, the main form of plastic deformation are folds. Folds can be anticlines or synclines. In this case, you're looking at an anticline. In this case, you're looking at a syncline. And they can have various geometries. The geometries to us aren't terribly important, except that in a geologic map, they don't always just show up perfectly upright and so forth. They can be plunging down into the ground or plunging up out of the ground. It can get pretty complicated. It's still a fold, though, ultimately. And so here's the Devil's Backbone just inside West Virginia down near Pocahontas County. Here's a monocline, horizontal rocks with a fold downward here, some location out west. These are both forms of plastic deformation caused by different mountain building events. Another way you could get some plastic deformation is just the upwelling of domes or the downwarping of basins. And you end up with geologic maps that look kind of circular like this, where the geologic formations, you can see them all around. This is the Michigan Basin. So the youngest rocks are actually in the center of the basin, and the oldest rocks are on the perimeter or more distal portions of the basin. Domes are the opposite. The oldest rocks end up showing up in the center because you've eroded off the top of a dome, exposing the older rocks beneath. once you've surpassed the elastic limit, and then the plastic limit, you end up with faults. This is where you break and brittly deform the rock, and you end up with either normal faults, reverse faults, or strike slip faults that are lateral, where you have lateral movement. In any of these cases, you're talking about breaking the rock, and you've put it through more stress than it can deal with before it breaks, right? And so this kind of thing can happen. And of course, the energy is never released just gradually. Typically, movement along a fault is sporadic. Call it episodic tremor and slip. And so the fault holds for a while until the stresses build up to a point where it can't hold any longer, and then it moves suddenly, and you get earthquakes. That's what an earthquake essentially is a release of the energy caused by that rapid movement. All of these things are caused by orogenesis. All of these forms of stress typically are put on rocks by orogenesis, which is just a big, complicated word that means the formation of elevation, orogenesis. And you're looking at creating mountains. And there's different kinds of mountains: fault block, folded, volcanic, and dome. We live in a region of folded mountains here in the Appalachians, but there are plenty of examples of fault block mountains if you go out west, the Grand Tetons and so forth. Dome mountains like the Black Hills and so forth. Volcanic mountains are pretty self-explanatory. This is how fault block mountains are created. You get one piece that's thrust up above the other side, and you end up, if that happens enough, you create mountains. And then, of course, fold thrust belt mountains are a combination of folds and thrusts, and you end up with a pretty complicated situation here. This is part of the story of the Appalachians, particularly the Blue Ridge portion of the Appalachians. Folded mountains are very typical of our area, hence the reason I put the picture of Massanutten Mountain over here and the Allegheny Front over here. You are here. This is King's Crossing over here, and this is probably then, actually Newmarket Gap is further south. All right, domed mountains are more like the Black Hills of South Dakota, where again you're going to see the oldest rocks in the center, and they'll look like this in cross section. So the Precambrian core of the dome, overlain by the sedimentary rocks that were deposited in an ancient ocean basin subsequently, but erosion has exposed all of it. How can we represent all of this? How can we tell these stories? How can we take a three-dimensional reality and make it into a two-dimensional map that we can all look at and enjoy and savor? So that's the goal here, is to really kind of go over how we use geologic maps to tell these stories. So how do we take this geologic map of the Middletown area, for instance, Virginia? How do we use it to tell the story of Middletown? I'm not going to sit here and talk you through it here, but you can give it. We're going to get into that in the next couple weeks. For some people, and you can pause the video here because it's kind of cool to look at this map. This is kind of how some people joke about geologists interpreting the history of the United States, the geologic environmental history of the United States. It's just a fun slide. But we live over here where there's government geologists and lots of overburden sitting on top of interesting stuff below, or folded stuff, right? It's a whole lot more interesting than that, I think. But first on the map, we use these things called strike and dip symbols, which I'm not going to play this video here, but basically you can search for this on YouTube, Geologic Mapping in Virginia. It's available there. We use this symbol that's got a little line that runs along. It tells you which direction the rocks are striking. I mean, if they're horizontal, they're not striking at all. But if they're dipping into the ground, strike is this direction, compass direction, usually represented as an azimuth from 0 to 360, that tells you the direction the rocks are moving on the map. And then the dip direction is the rocks, the direction in the compass terms that it's dipping into the ground, northwest, southeast, that kind of thing, and how many degrees from the horizontal it's doing that. All right, this allows us to think about things spatially in more context. And it gets, this is sort of a summary of some of the basic geologic map symbols. I'd pause here for a bit to sort of take it all in, but these are some of the symbols you're going to run across. We have different kinds of symbols for domes and basins, and the different kinds of folds and faults, whether we think there's a contact there or not, or can confirm that there's a contact there, dash line, solid line. things of that nature. So there's a whole lot of different symbology that you're not used to. But the main symbology that you need to be familiar with are these strike and dip symbols, and there's various forms of them depending on the situation. So it's worth spending some time on this slide. Map scale is critical, of course. It tells us something about how large distances are and areas are on a map. And of course, you should be familiar with this already, being able to actually use a scale. Normally, I would teach about UTM coordinates as well. I'm not going to worry about that right now because we're not going to deal much with that beyond that. But geologic maps and USGS topo maps are provide the foundation for the geologic maps typically, and they are delineated based on latitude and longitude. They're typically referred to as 7.5 minute quads, but they can come in other scales as well. But UTM coordinates are always available on them as well. So here's a geologic map. This is a really complicated one because it's full of igneous and metamorphic materials, and oftentimes they make maps that look like this, and they're difficult to interpret. I'm not going to give you one of these to interpret because it's frankly really complicated. Although, you have some sense of how old things are based on the symbols that are being used. Q typically stands for Quaternary, and then you'd find the symbol and you'd find the formation in the key where it gives you an idea of the age of things, and you can start to interpret the age of things. This is out in the Santa Fe, New Mexico area, where the Sangre de Cristo Mountains. My first week of geologic mapping during my field school was actually up in the Sangre de Cristo Mountains, and it was complicated. It was fun, but strangely enough, that was our first week of mapping, and we did the easier sedimentary stuff later on. It's just an interesting way of doing it. That was State University of New York at Buffalo ran that field school. This is a portion of a geologic map in the Monterey, Virginia area, and typically when you see layers that are just kind of striped like this, you know that they're not horizontal; they're jutting out of the ground somehow, and you're seeing layer after layer of stratigraphy. That of course, this is O for Ordovician, and then of course S for Silurian, D for Devonian. You begin to put together a history here based on what you see in the key for the map and what these symbols mean and the colors. But this is a folded mountain range, and this is typical of what that looks like. This is a fault. It's not a cold front. It's a fault. So this is what these things begin to look like. This is a generalized geologic map of Kansas. Not terribly exciting, but you can see the layers are much wider, and that's because largely Kansas geology is pretty flat. It's not perfectly flat, but if you look at the cross section, there's not a lot of topography or not a lot of tectonic change here. There's a little bit of upwarping here, but that's largely pretty flat. And of course, this is out in Oklahoma in this case, this map that's popping up here. But this is a dissected area where the layers are flat, but the topography has been heavily dissected by water. And so this is typical out in western West Virginia as well. And of course, another couple places that have relatively flat topography, Indiana and Ohio. Most of what you're seeing here, for instance, this big thing going on over here, this is the glacial margin. That's as far south as the glaciers went during the last glacial period. But all of this has been exposed by glaciers eroding it. And so that's why we see it. Otherwise, Ohio would be largely one color because it wouldn't be all that exciting. Here's a cross section for it, just a big, large dome, essentially. Here's a geologic map of Virginia. Compare that to these, it's a whole lot more complicated because you have a number of different orogenic events occurring because Virginia is on the coast of a major continent. So we've got a lot of stuff going on here. But West Virginia gets a little less complicated, but you have some remnants of Virginia geology before you get over into the stuff that's more like Ohio. This is a geologic map of the Valley Range of Pennsylvania. Again, it's the same Appalachian Mountains we have here. So you get this striping that's pretty typical of a folded mountain belt. But in this case, the folds are plunging in and plunging out of the ground, and you get these kind of things that look like the points of arrows as a result of that. And so when I talk about plunging, here's an anticline and syncline plunging away from the viewer. This is like what you just saw on the prior slide. This is the surface here. Then this is typically what you see with plunging folds, but there's not a lot going on the surface and so forth, or doubly plunging folds where you end up with domes and so forth. And then, of course, just you could pause here and get an idea what some of the symbols mean and what they look like in 3D, and so forth. You can do that with each one of these slides. So this is just more of an overview of geologic map symbols and what they're trying to represent in 3 dimensions. Ultimately, another form of deformation that's important to keep in mind are just the tectonic areas in general, based on the 3 types of plate boundaries that we have, as well as the geotherm. And the geotherm is different at different kinds of tectonic situations. So, like at mid-Atlantic ridge areas, it's much hotter, much quicker as you go down, and so that, of course, can have an effect um, on rock because you in a very short depth you end up with a great deal of heat, which can actually start melting rock really quickly, as opposed to a normal situation where you never actually reach the point of melting. It'll get hot and hot and hot down below Virginia, for instance, but never actually have anything molten down there. Oh, this isn't important. All right, that's going to take us to. I'm going to go to one last slide here if I can, and that's just these are the different kinds of tectonic stresses that can occur as a result of different types of plate boundaries. So, all right, I'm going to stop things there, guys. That's a lot to take in, but it should help you with your explorations of geologic maps this week.